Okay, let's talk torque. Torque is the rotational equivalent to force. So in other words, we're talking about torque when we're causing objects to spin. And torque by definition is force times lever arm. You also see that written as F times R. At some point in time you talk about cross products and stuff like that as you go farther, but you can really write it either way. I'll probably try and write it that way as much as anything. But the force times L for lever arm kind of makes sense. So if I have an object like this is my pivot point. If you're going to have something rotate, it's got to have a point at which it rotates around. A force out here will cause it to rotate, and it's going to cause it to rotate this way, which of course would be, if this is the center of the clock, it would cause it to rotate in the same direction that the hands would go, so this would be a clockwise torque. If you applied a force this way, that would cause it to rotate this way, which is of course counterclockwise. So you decide directions by figuring out, is that the only thing that's acting at that point? Okay, so let's look at how to calculate that. So let's do one. Let's take an object P. We'll have it like this, and I'm going to apply a force to it. But this time I'm going to do something a little bit different with the force. I'm going to apply the force back in an angle that way of, let's say, 60 degrees. Now, the key thing to understand with torque is equal to force times R, but it's the force perpendicular to the motion. So, and that's kind of important, although I'll show you a shortcut you can use in just a minute. So, in other words, it's really only this side of the triangle. So it's force perpendicular to the motion. Now you can also draw it over here. It really doesn't matter which place you draw it. Right there it would be the force perpendicular to the motion. You can do it that way. Either one would work, and you would have the same value. Now to figure out what that is, there's two ways to figure out force perpendicular. If I use this triangle, I would say, okay, well obviously the hypotenuse is my F, and it's some portion of F. So therefore, and it's opposite of the angle, so I would say the sine of 60 degrees is equal to force perpendicular divided by F. So when you multiply force perpendicular, then would be equal to F times the sine of theta. Now the sine of 60 degrees is 1/2, so it would be F perpendicular would be 0.5 F. Now in a real problem you may be given what F is, so it could be done that way. Now you can also use this triangle out here if you want, but you have to realize that then now this is equal to 30 degrees because these two have to add up to 90. So now I would say that, okay, well this is still my hypotenuse, but now this is the adjacent side, so I could do cosine, but now it's the cosine of 30 degrees is equal to F perpendicular divided by F, so therefore F perpendicular is equal to F cosine of 30 degrees. And of course that's also 0.5. So that. Now, let's take a look at what happens when I get multiple torques involved. Well, if I have multiple torques, then I'm going to have some type of net torque. Let's go back to the blue pen. I'm going to have some type of net torque. Now, the net torque can either be equal to 0. That's if we have something that is not spinning, or constant spin. Or I can have a net torque that's equal to I times alpha. In other words, now what's going to happen is this is going to be accelerating. It's going to have an angular acceleration. So in other words, it's spinning faster and faster and faster and faster and faster. Most of the cases you're going to encounter are that. But I'll show you how to do both of them. So let's take a board, and let's just put a board there, and let's put a 2,000 Newton person out here. That's a seesaw. And over here, I'm going to put a 1,500 Newton person. And I want to figure out what's the sum of the torques. What's the net torque? Well, if I look at this way, well, we know torque is force times lever arm. So the torque from this person is 2,000 newtons times 1 meter. And I know that that's the torque on that side. Now, if I cover up the rest of this, and this is the only thing acting on it, this is going to cause it to go this way, which is counterclockwise. Now, I can easily call that direction positive, so I'll make that one positive. Now, if I come to the other torque over here, let's decide direction first. If this is the only torque acting on it, it's going to cause it to go this way, which is clockwise. So this one over here is counterclockwise. This one over here would be clockwise. So since I said this is positive, then I have to say minus 1,500 newtons times 1 meter. That's all equal to the sum of the torques. Well, that's 2,000 minus 1,500, so I have 500 Newton meters is the sum of the torques, and positive 1, so therefore this is counterclockwise. You can see that. Now let's go to a wheel, since that seemed to cause a little bit more difficulty, and let's do this. That's R. That's 2R. And I'm going to pull it that way with a force of 3F. And I'm going to pull this way with a force of 2F. And I want to find the net torque equals my unknown. Now, the first thing I would probably do with something like this is I would say, okay, what direction am I going to cause positive? And you make that decision. So if this is the only force acting on it, in other words, I cover up the other force, it's going to cause it to rotate in that direction. So this one's going to cause it to go that way, which is, of course, clockwise. So let's call that positive. So on the clockwise torques, I have, well, it's going to be the force times the distance away from the pivot point. Well, the pivot point is right here, so the distance is actually 2R. So let's go torque from the 3F is equal to 3F times 2R. So 6FR from the 3F. Now, we also have this one down here. Now, if I take a look at this one, I, again, ignore the rest of them. What's going to happen? Which way is this going to cause it to spin? Well, it's also going to cause it to spin this way. Well, that's also the same as a clockwise, so that's also a positive one. So now what I'm going to do now is I'm going to say, okay, the torque from the 2F one is equal to 2F times R, which is 2FR. Now, since they're both in the same direction, my net torque is 8FR. So it's not too bad. Now, they can play around with angles and stuff like that, but it's not too bad. Now, let's try one last case. This one last case is what happens if I have something balanced that's not at the center. Let's take a 6 meter long, and let's make it 100 kilograms. And what I'm going to do is I'm going to force it to where it can rotate around this point. So that's my pivot point right there. And then what I'm going to say is, okay, let's put a 500 Newton box out on the end of it. And what I'm going to say now is, okay, I want to find out the net torque. Now, remember, if you have a 6 meter long rigid rod, the center of it is going to be right there at 3 meters away, and I can treat the entire 1,000 newtons as if it just acts at that point. You can turn the lights on if you need to.
No. I was wondering, who was you talking to?
Talking to the computer. So I can get the torque from that one. Now, if that's the only thing acting on it and it pivots around this point, this is going to cause it to spin that way. So let's go ahead and just call that positive. Now, if I have this point acting out here, and let's say it's acting all the way out at the end, and so out here I have 500 newtons acting down. Well, that's also going to cause it to spin this way. That's the reason I'd have to have some type of upward force for it to be in equilibrium, but I've got a net torque. So, well, my net torque is going to be, well, the first one is 3 meters away. The second one is 6 meters away. So I'm going to say 1,000 newtons times 3 meters plus, since they're both in the same direction, 500 newtons times 6 meters. Well, that's 3,000, so is that. So my net torque is 6,000 Newton meters. Now, if one of these had been going in the other direction, that would simply change the sign down there to a negative sign. It doesn't change anything to it. Now, there's a separate video on it, but net torque is equal to I times alpha, because if there's a net torque, it's going to accelerate. The same way in the linear world, if there was a net force, it caused the object to accelerate. So the analogy is there. Now back to our original torque question. We said torque is equal to force perpendicular times R. There's a shortcut that you can make sometimes that might make your life easier. Torque is also equal to force times R perpendicular. And both of those work. In class I'll show you how to make those work because I want to show it to you as we do it. Okay, hope that helped.